For the first talk of today, we will welcome William Dana from University of Michigan in Ann Arbor, and he'll be talking with us about stability of stretched root systems.
Thanks for the introduction, and good morning, everyone. Thanks for coming to the talk. Today I'll be saying a bit about this preprint I put up on the archive a few months ago, examining this stretching operation on root systems, which seemed interesting. So I want to start out by laying out the sort of big picture general motivation for what I'll be talking about here. And it comes from the theory of Coxster groups. So we can associate to any Coxster group its Coxster diagram, which is just going to be a graph with integer labels on some of the edges like these ones. And you can make a Coxster group out of any diagram, but there are two important special classes, the finite Coxster groups, and then also the affine Coxster groups, which are just barely infinite in a way that's still tractable. And in both of these cases, there's a nice classification of which Coxster diagrams can show up. There are some isolated exceptional examples, which I haven't shown on this slide, and then there are some well-behaved infinite families, which is what I have shown here. And what's interesting about these infinite families is that their diagrams are all constructed in pretty much the same way. You're starting with a simple diagram, and then you're inserting a path into it. You can think of this sort of as like building all of these families on the type A family, where the diagrams are just paths, like so. So this is a construction that we could perform on pretty much any graph, as long as we include a little extra data. So if we're given an arbitrary Coxster diagram G, a particular vertex X, where we're going to do this path insertion, and then a partition of the neighbors of X into left neighbors and right neighbors, LX and RX, then with that data, we can construct a family of stretched diagrams, which I'll denote stran of G, in just the same way as on the previous slide. We replace X with this path, I'll say of n+1 vertices, hook up the left end of the path to the left neighbors, the right end of the path to the right neighbors. And you get a family of diagrams just as before. So once I have a family of diagrams in this way, this will give me a family of Coxster groups. But on top of that, there are lots of other objects which are associated to these diagrams, sometimes with a little more data, but sort of in this general Coxster space. So things like root systems, cluster algebras, and quiver representation categories, if you're including a choice of orientation, lots of other objects as well. And in general, the objects in these families so I'll get families of all these types of objects. In general, the individual objects in these families will be very poorly behaved. Because outside of the finite and affine type cases, generally many aspects of these objects are either extremely complicated or provably intractable. But there are a couple of vague motivating questions which I think are reasonable to ask about sort of common behavior throughout the entire family. First off, do these families exhibit some kind of type A behavior? Is there some sort of analogy with the very well-behaved type A family of objects in each of these cases, which reflects the way we constructed these Coxster diagrams? And secondly, are there properties of these families which stabilize when n gets large enough, when the stretching factor gets large enough? Are there properties which exhibit some kind of nice uniform description? And so this level of generality is something that I haven't seen show up that much, but there are a couple of examples of this I've seen in the wild. In 2016, Richard Hepworth considered the specific example of appending just sort of a tail onto a particular vertex of a diagram, and showed that the Coxster groups, which you obtain in this case, satisfy homological stability. They're group homology stabilizers. And then there are a couple of papers of Chen and Krause in 2010 and Puckeneger, Kalk, and Plug in 2019, who both consider relationships between abelian and triangulated categories of quiver representations, other representations of path algebras, considering operations which they called expansion and AN insertion, respectively, which have this effect sort of on the underlying quivers of these categories. And if you've seen other examples of this construction in the wild, I would love to hear about it. So I also came to this from the direction of representation theory. I was interested in studying the representations of pre-projective algebras, a type of path algebra. But in doing so, I was led to some purely combinatorial questions about Coxster groups and root systems, which seemed independently interesting. And so I'll talk about, I have a couple of those things. I'll talk about one of those here. I don't have time for the other, but it's in the paper I mentioned up front. So I'm interested in talking about Coxster groups and root systems. If you're not super familiar with the notion of a Coxster group, I'm afraid I don't have time to go into much detail describing it, but you can think of it roughly as a group which is generated by reflections. You'll have one generator for each of the vertices of your Coxster diagram, and then you'll have these acting by reflections. And when I say reflection, you can think of this as essentially a linear involution which fixes a hyperplane, which reflects across a hyperplane somehow. So here I've shown the A2 Coxster diagram and the presentation of its associated Coxster group. This is, in this case, the dihedral group of the triangle or the symmetric group on 3 letters. And a nice geometric picture we can make of a Coxster group is to look at the hyperplanes fixed by each of the elements that acts by a reflection, including both these generators, which we're defining essentially to act by reflections, but also any conjugate of the generators, which will act by reflecting across the appropriately different reflecting hyperplane. And one way of then thinking of the root system associated to the Coxster group is that the roots are vectors in the dual space which are dual to these hyperplanes. Or more concretely, you can think of them as the equations which cut out these hyperplanes. So here in this picture, I have my 2 generating reflections, the 2 diagonal hyperplanes correspond to the generators S1 and S2. Those are associated to my simple roots alpha 1 and alpha 2. And then I'll have a third reflection, which ends up corresponding to, in the dual space, the sum of those 2 roots, alpha 1 plus alpha 2. And I'll say that that is a root as well. Now, as I've stated it here, this isn't actually well defined. It's only defined up to a scale factor. So more precisely, a way of defining roots is to start with this basis of simple roots in the dual space, picking out simple roots associated to the generating reflections. These will be alpha 1, alpha 2, etc. And then apply the contragradient, the dual action of the Coxster group in order to build up all of the other roots. One small technical point I should mention, and so here we see the example of we can build up this alpha 1 plus alpha 2 as S1 of alpha 2 or S2 of alpha 1. And you can see that visually in the picture by noting that if we reflect the alpha 1 hyperplane across the alpha 2 1 or the alpha 2 hyperplane across the alpha 1 1, we will get this third hyperplane in the middle. One small technical point I need to mention here is that these roots will come in opposite pairs of positive and negative roots. I'll have alpha 1, but also minus alpha 1 plus alpha 2, but also minus alpha 1 minus alpha 2. And for the rest of this, I'll only be talking about the positive roots, the ones with non-negative coefficients. So that's the basic language I want to talk about here. Now, if I want to talk about if I want to find some sort of stabilization phenomena for root systems, then one way of looking for this is to come up with a way of embedding the root system I start with, associated with the diagram G, into the root systems of the stretched diagrams. Or to put it another way, for each root of the original diagram, find counterparts in each of the stretched diagrams. And there is actually a very natural way of doing this, which I'll explain now. So as I mentioned on the previous slide, we have this natural basis of simple roots corresponding to the generating reflections. And we can write any root in the basis of these simple roots. But these simple roots are also associated to the vertices of the Coxster diagram, or the simple roots are associated to the generators, which are associated to the vertices of the Coxster diagram. And so we can depict any root as a function on the vertices of the Coxster diagram, just by recording its coefficients on the vertices. So here I've shown what that looks like, again, in the simple case of A2. And once we have this visual presentation of the roots, then this gives a very natural way of embedding this root system into its stretched versions. Essentially, we just take the coefficient which appears at the vertex we're going to stretch, and we repeat that coefficient on every vertex of the stretched path. And so it's, as it is, I've only just defined a function on the vertices of the stretched diagram, but in fact, it's not complicated to show that this is also a root of the appropriate root system. And for instance, in terms of the connections to representation theory of path algebras, this is sort of like replacing a vector space in the middle of your path algebra with like a chain of vector spaces with linear maps, if that's a context you're familiar with. But anyway, so I have this notion of embedding a root system into its stretched versions. And so that gives me the ability to talk about sort of how different constructions associated to individual roots stabilize as I stretch out the root systems and the roots within them. And so I'll talk about one of those constructions now. So this concerns the root postset associated to the root system. This is a partial ordering of the positive roots, in which we say that alpha is less than beta if there is some sequence of generating reflections I can apply to alpha to get beta, such that at every step of those reflections, I am increasing a coefficient of the root. So this is saying I can get from alpha up to beta sort of by a minimal sequence of reflections in this way. And I should warn you now that there are at least two definitions of things called the root postset, and this is actually the slightly less popular of those two. But it is still one that's considered. It shows up, for instance, in Bjorner and Brente's combinatorics of Coxster groups. And so I've shown, for instance, the root postset of the A3 Coxster system on the lower right here. And one nice way of sort of carving out chunks of the root postset to study, in general, like I've been showing finite examples, in general, the root postset is going to be horrendously infinite. But one way of carving off nice chunks to study is to look at the downsets in the root postset, where I just fix a root alpha and I look at all of the positive roots in the root postset, which are less than or equal to alpha. So in a way, you can think of this downset as sort of encapsulating all the different ways of building up alpha starting from a simple root. Chains from a simple root up to alpha in the root postset correspond to sort of minimal sequences of reflections that get up to alpha. And so this will encapsulate all of them and give you sort of an idea of all the different ways of building up that root. So I have this definition of the root postset, and once I have this, that brings me to sort of the main question I'll address in this talk, which is, here's a construction I can associate to a specific root, alpha. What happens to the downsets of these stretched versions of alpha in these stretched root systems as my stretching factor n grows? And the answer to this ends up passing through a notion which I call a stretching class. So this is going to be, this is something that's really fiddly to actually define in words. So I'm going to hope that a pictorial definition gets the point across. Essentially, a stretching class is going to be defined by a notation like the top thing here, which looks somewhat like a root on some stretch of the diagram, but with asterisks applied to some consecutive sequence of coefficients on the stretched path. And I'll say that the stretching class that notation specifies is the collection of all roots on all stretches of my diagram on which the asterisked coefficients are allowed to repeat any number of times. So for instance, the notation I'm showing here defines sort of this class of all roots of sort of any stretch factor on which I have on the stretched path some number of 6s, some number of 5s, and then exactly 1 7. And then the coefficients off of the stretched path are fixed. So this gives me sort of families of roots that persist through all of the different stretches of the root system, and that allows me to state a theorem which answers this question. So we fix a Coxster diagram G, some of the stretching data of a vertex where we're inserting the path, the left vertices, the left neighbors and the right neighbors of X, and we fix a root of the original root system, a root alpha of the original root system. Then there exists a finite set of stretching classes which describes the downset of stir n of alpha for sufficiently large n. Once n gets large enough, sort of the ways in which the paths you can go through in order to get to stir n of alpha in the root postset, the ways in which you can build up stir n of alpha from a simple root are sort of specified by this finite collection of information through these stretching classes. And maybe this is a little abstract on its face because I've only just defined what a stretching class is, but a concrete enumerative consequence of this is that the number of roots in the downset of stir n of alpha is going to be given by a polynomial for sufficiently large n. So this result gives sort of a weak form of the type A behavior, which I mentioned as a vague goal at the beginning of this talk. Because if you look at the finite type families of root systems, the number of roots in each one is a quadratic in n. You can think of these root systems, in general, there will be a highest root or two highest roots, I think, in type B. But in general, sort of you can view them as downsets entirely. And this is saying that the size of those downsets is quadratic in n. In general, then, it will be a polynomial, but potentially of higher degree than a quadratic. So looking forward, there are some other interesting questions which you can ask from this perspective. One thing which I find interesting is to ask, are there similar results for this similar results to this on the weak order on Coxster groups? This is an order that's defined very similarly to the root postset, but it's on the elements of the group rather than on the roots of the root system. So this is more complicated in some ways. In the finite type case, it just has many more elements, and it's a little less clear how it should interact with stretching, but it's also a similarly defined postset, and so it seems like also an interesting thing to consider. And then the second result in the paper I mentioned at the beginning, which unfortunately I did not have time for today, but is sort of related to these questions of how does this stretching operation interact with the representations of path algebras and pre-projective algebras. There are some enumerative clues coming from Nathan Reading's theory of shards. This is a breakdown of the reflecting hyperplanes of the arrangement into cones, which was originally introduced to study quotients of the weak order, but which also these shards are in correspondence with certain interesting representations of the pre-projective algebra associated to the graph. I have a nice enumeration again and a uniform description of these shards, but it seems interesting to consider sort of, is there a similar uniform description of these representations of the pre-projective algebra? But anyway, that's all I have time to talk about here. So thank you again for attending.
All right, everyone, please unmute yourself or use a clap symbol, whatever, to thank our speaker. Is there any questions from the audience for the speaker? There's a question in the chat.
Oh, thank you. Kayla asks, can you say a bit about the cluster algebras associated to these stretched root systems? Do they have any nice properties? I have not looked at the cluster algebras angle at all. I imagine that is a very interesting thing to look at. But I imagine it could also get very fiddly. In general, sort of the tool that's useful for considering the stretching operation on root systems is to sort of use the fact that complicated stuff might happen at the ends of the stretched path, but sort of passing information back and forth along the stretched path can only happen in a prescribed way. But if you're doing quiver mutations at the vertices of the stretched path, it's possible that it might get more complicated. But again, I haven't looked closely enough at it to speculate about that. Thanks for the question.
Any other questions? So you say one of the further direction that's possible is to look at the weak order on Coxster groups, right? Have you looked at like the very smallest case, for example, like A3 that you just talked about? Like, is it any difference between the weak order case or the root postset case?
I mean, it is very different because, for instance, the type A Coxster groups, the size is n factorial, but the root system grows quadratically. So it's just a much bigger postset. There's sort of, there's just sort of more elements to keep track of. And in particular, it's, and like I have sort of looked at some preliminary examples of like just what happens when you compare the weak order of A2 to the weak order of A3. Mm-hmm. So already, although there's a natural notion of stretching, it doesn't respect the weak ordering necessarily, and there's no immediately obvious structure that should be coming from there that's analogous to sort of how we get an embedding of root systems in the root system case.
I see. Thank you. Right. Any other questions from? Oh, there we go.
Oh,
so there's another question in the chat.
Does the stretched root postset have any nice postset properties you've explored? I mean, postset properties is a vague question. I would consider this description of the downsets to be a nice postset property. And in general, you can sort of like look at individual, like sort of cover relations in the starting postset and see sort of how what happens to sort of the top and bottom and the interval between them as you stretch. One thing that's slightly awkward is that they may actually not remain comparable as you stretch, but you can still say sort of if you take any given cover relation and perform this stretching and look at the interval between the two stretched roots, then there's sort of like only 3 different patterns which can appear there. So there's maybe a sense in which this root postset can be like built up from blocks which are based off of these 3 patterns. I imagine it's a little subtler than that. But it's not the ultimate niceness because, for instance, elements may not remain comparable when you stretch them in this way. And that's sort of the one snag that makes proving things here a little difficult.
All right, awesome. So let's thank the speaker again for all the questions. If you have further questions, feel free to refer to the speaker individually.